Hey, Global Impact, this is Mr. Ellinger here. This lesson is on standard form of a quadratic function. Our learning target for the lesson is we want to be able to graph quadratic functions written in standard form. Some essential understanding for you for the lesson. Any quadratic function is a stretch, compression, reflection, and or translation of the parent function y equals x squared. The standard form of a quadratic function is f of x equals ax squared plus bx plus c, where a cannot equal 0. For any quadratic function f of x equals ax squared plus bx plus c, the values of a, b, and c provide key information about its graph. Standard form is what we call calculator ready in the transformation of y equals x squared. Some background knowledge for the lesson. Note that we must put the stipulation that a cannot equal 0 in the standard form of a quadratic function, because if a were to equal 0, then the function would be a linear function and not a quadratic. A, B, and C provide the following information about the graph of a quadratic. It tells us whether the graph opens upward or downward. A tells us that. The coordinates of the vertex, A and B, help us determine that. The axis of symmetry, which comes from the x-coordinate of the vertex, and also the y-intercept, and C helps us do that. All right, so in the first lesson here, we looked at quadratic functions written in vertex form. Now we will use quadratic functions in standard form. And again, we talked about what the standard form is. So we can find information about the graph of a quadratic function, such as the vertex, easily from vertex form. Such information is more hidden in standard form, but we have some tools that we can use to get this information out of the equation. But like we said, this form is what we call calculator ready. It's easier to enter into a graphing calculator to generate the graphs of these functions. So here's an example, a screenshot of a calculator, and the function y equals 2x squared plus 8x minus 2. So we can, once we get that graph on there, we can discuss some things, range, vertex. We can get the information from the graph, and we have in our menu option, once we graph a function, when we start analyzing a graph, we can find things like minimum and maximum. We can find x-intercepts, y-intercepts, and things like that. So we'll kind of take a look at some of those tools. All right. So we can find information about the quadratic function, the standard form, from the coefficients a and b, and from the constant term c. So this box here kind of outlines those things. So we know that the graph of f of x is a parabola. If a is greater than 0, the parabola opens up. If a is less than 0, the parabola opens down. Here's where we get into the tools that we need if we're working with the equation in standard form or function in standard form. The axis of symmetry is the line x equals negative b over 2a. And b and a just come from our standard form. The x-coordinate of the vertex is negative b over 2a, and it makes sense that the x-coordinate of the vertex is the same as this formula, if you will, for the axis of symmetry, because the axis of symmetry runs through the x-coordinate. So this is like a little formula for finding the x-coordinate and also the axis of symmetry. The y-coordinate of the vertex is the y value of the function for x equals negative b over 2a, or we can say y equals f of negative b over 2a. It's the value of the function at that x-coordinate of the vertex. And then this other thing, we have the y-intercept is 0c. Now, why is that? Well, if you think about it, if I have my function and a y-intercept, we know that x is 0. So really we're trying to determine where is f of 0. Well, if I put 0 in for all my x's, what am I going to be left with? This is all 0, this is all 0, I'm left with c. So 0c is always going to be the y-intercept. Okay, so here's why this works. You can expand the vertex form of a quadratic function to determine properties of the graph of a quadratic function. So here's what I'm going to do is I'm going to start off with vertex form, and I'm going to rework this to show you why this stuff works in standard form. So if I just kind of simplify vertex form a little bit, meaning square my binomial here, I get a times the quantity x squared plus 2hx plus h squared plus k. Distributing the a to all those terms, I get this next line. And then if I collect my like terms, simplify this a little bit, I get this function here, a times x squared plus the quantity negative 2h, that times x, and we kind of separate this out for a reason, plus the quantity ah squared plus k. Now that shuffling of things around, if you notice, the reason I did that is because I had one term with x squared in it, I had one term on x, and then I had an ah squared and a k. Those are all constants. Those are all just numbers. They have no variables in them, so that's why we kind of separated these here. So if we compare this to standard form, a equals a, b equals negative 2ah, okay, which generates negative b over 2a equaling h, if we solve that for h. So that's where it comes from. H, which we know is the x-coordinate of the vertex in vertex form, can now be thought of as negative b over 2a in standard form. So that's where that negative b over 2a comes from. So here we have our comparison. Vertex form on the left, standard form on the right. Okay, so that's the algebra on why that it is what it is in standard form. So what is the graph of y equals negative 2x squared plus 2x minus 5? Well, right away, just by looking at our equation, we know that this is going to be a parabola that opens downward. So right away we know that our parabola is going to have a y-intercept of 0, negative 5, because c is negative 5. So I could go ahead and plot that point on my graph. So now what I'm going to do is I'm going to determine the axis of symmetry and also the x-coordinate of the vertex. I'm going to use my formula x equals negative b over 2a. And in this problem, a is negative 2 and b is 2. Okay, now this is where we just have to keep track of our signs here. We have a negative sign here. B is 2 times 2 times quantity negative 2. All right. And using parentheses around all values substituted into an equation, I have a negative, I have a 2, and then on the bottom I have a negative 4. So what does that wind up being? Well, this negative out front here, and combined with, if we have a negative in the top or the bottom, not both, but one or the other, we're going to wind up with a positive value. So this winds up being positive 1/2. So the x-coordinate of our vertex is 1/2, and our axis of symmetry is x equals 1/2. So x equals 1/2 is going to be a vertical line that goes through 1/2, which is here. So I'm going to go ahead and put my axis of symmetry on here as well. We usually use a dashed line to represent that axis of symmetry. So right away I know another point on my graph, don't I? The y-intercept is 1/2 of a unit to the left of the axis of symmetry, so I'm also going to have a point here. Now I need to know the value of this equation or function, so I need to know f of 1/2. Remember, y and f of x we can use interchangeably. So I'm going to have negative 2 times the quantity 1/2 squared plus 2 times 1/2 minus 5. Here I got to be careful. I've got to square 1/2 first, which is 1/4. When I multiply that by negative 2, I get negative 1/2. 2 times 1/2 is 1 minus 5. Okay, so this is going to be negative 4 1/2, or negative 4.5. When I simplify that, okay, so 1/2 negative 4.5. So I could just make this in decimal form. And there's my vertex. So 1/2 on my axis of symmetry, go down to negative 4.5 on the y-axis. This is getting kind of tight here, but there's where my vertex is. Okay, so I can see where the u is. I can see where it tops out in this case because we know it's opening downward. I probably should go ahead and just get another point here. So I'm going to use 2, another point to the right, or another x value on the right of the axis of symmetry. And I'm just going to evaluate the function for x equals 2. So negative 2 times 2 squared plus 2 times 2 minus 5. I get negative 2 times 2 squared, which is 4. That's negative 8 plus 4 minus 5. I get a value of 9, negative 9. So another point on my graph is 2, negative 9. So let me plot that. 2, negative 9 would be here. And that point is 1.5 units to the right of the axis of symmetry. So I'm just going to go 1.5 units to the left of the axis of symmetry and get another point. And now I can kind of see where this U-shaped curve is defined. So I will just do my best to draw a U-shaped curve that goes through those values. So that's what my graph looks like, okay? So then once we get the graph, we get to answer some questions like, what is the range of this function? Okay, what is the range? What is the domain? The domain on a quadratic, again, all real x. So we can write that out, all real x. If we want to write our domain as an interval, we would write this as negative infinity to positive infinity. The range of this, if we were to write this, there's two ways to write these. You can write them as an inequality. I could have written this as an inequality up here as well. Let me write that as an inequality. Okay, here is the domain written as an inequality. In words, interval, inequality. The range, since it's not all real x in this case, I'm going to go ahead and write it either as an inequality or as an interval. So how would I represent this as an interval? So the range are all values from negative 4.5 to negative infinity, right? Everything less than negative 4.5. So the way that I write that as an interval is everything from negative infinity up to negative 4.5, including 4.5. We always put a parenthesis on negative infinity. So there's my range as an interval. And then how I write that as an inequality is I can use y. Y is going to be less than or equal to negative 4.5. So that's how I could write my range as an inequality. What is the vertex form of y equals negative 2x squared plus 10x plus 7? So we're given an equation in standard form, and we want to transfer that to vertex form. So again, in standard form, we can identify these coefficients a, b, and c. And if you remember, a and b help us determine the x-coordinate of the vertex, which has a different assignment in the vertex form, but we can go ahead and determine the x-coordinate of the vertex using our negative b over 2a. And when we do that, we find that the x-coordinate of the vertex is negative 2.5. If we substitute that value into the equation and simplify that, we get a y value of negative 5.5. So the vertex for this parabola is negative 2.5, negative 5.5. In the vertex form, that's our h and our k. All right? And we already know a we can get from the standard form. So we just go ahead and substitute those values in. Here's our vertex form. We're going to substitute 2 in for a. We're going to substitute negative 2.5 in for h. Now notice this minus sign is already there, and I'm substituting in a negative value, so we got to be careful here. And then put negative 5.5 in for k. And then just simplify this a little bit here, this 2 sign business. If I'm putting a negative number into the form, then the outcome is going to wind up being positive after I simplify that, okay? So there's our vertex form. So we can go from standard form to vertex form fairly easily. We just have to identify the coefficients in standard form, use our negative b over 2a to find the x-coordinate of the vertex, which then will lead us to the y-coordinate of the vertex. Then we can go to the vertex form. And then we also saw earlier that we can go from vertex form to standard form just by expanding the vertex form out. Okay, so here's an application. The problem says the New River Gorge Bridge in West Virginia is the world's largest steel single arch bridge. You can model the arch with the function y equals negative 0.000498 x squared plus 0.847x, where x and y are in feet. How high above the river is the arch? How long is the section of bridge above the arch? So here we have a picture of this. So we have the height of the arch. Okay, we have the length of the bridge above the arch. So we are told that where the arch goes into the ground, that distance from that point down to the ground is 516 feet. That wasn't mentioned in the problem, but that is in the diagram here, so we need to use that. So if we just take a look at the no need plan phase of solving this problem, and this should always be our thought process. What do we know? What do we need? And then a plan. So we know that a function that models the arch and the vertical distance from the base of the supports to the water, we know that stuff. We're given that in the problem. What we need is the height of the arch above the support base and the length of the bridge above the arch. That's what we're asked to find. So a plan would be to find the vertex. The y-coordinate is the height of the arch above the support base. The x-coordinate is half the distance between the supports. So you can see here in the picture, we have our parabola shape being modeled here, okay? Sometimes we use parabolas to model projectile motion. We'll look at some examples of that. This is a little bit different. This is looking at a side view of this bridge and modeling the shape of the bridge with a parabola, and then you could transfer that picture onto a coordinate plane and analyze it and use some math. Engineers and things could do that when looking at the properties of this bridge. So to find the vertex of the arch, here's what we did. When we were told the equation, the difficult part of this problem would be to generate the equation that models that parabola. Without that, we'd kind of be stuck here. But we can find the x-coordinate of the vertex from our equation. Okay, so here we're plugging in our values into that form, and we get approximately 850 for the x-coordinate of the vertex. If we substitute that value in for x, solve for y, we get 360. So the vertex is about 850, 360. Okay, so taking a look at this arch on a graph, on a coordinate grid, if our x-coordinate is 850, so here's along our x-axis, we're 850. And then our y-coordinate is 360, so here is the arch on a graph. So that information, we just found the height. The height is 360 feet, okay? And this x-axis, if I go back to my picture, the x-axis is basically running right here. Okay, this horizontal distance between the support bases, where the support bases are anchored into the ground. That's our x-axis, okay? So we find the height of the arch above its supports, and again, that's the y-coordinate here above the x-axis, 360. So find the height of the arch above the river. Well, if we go back to the picture, we remember that we were told that the supports are 516 feet above the ground. We know that our arch is 360 feet tall, so total above the river, if we add those two together, we get 876 feet above the river. Find the length of the bridge above the arch. Well, if we I'm not going to go back to the picture here, but if you remember, diagram here, it's kind of broken up into this right here, right? The length of the bridge above the arch has two components here, from the vertex to the left support base and then to the right support base, okay? And the nice thing about having this on the graph is we actually know that this distance here is 850. That's the x-coordinate of our vertex. And so that vertex, since it is 850, we know that it is 850 units away from the y-axis on our graph. And that's half the distance, again, using this concept of symmetry. So the other half of the distance of the length of that bridge above the arch support is 850 as well. So 850 plus 850 is 1,700. And our units in this problem are feet. So we know that our arch is about 876 feet above the river, and we know that the length of the part of the bridge above the arch is 1,700 feet long. Okay, so there's a very nice application of quadratics, and like I said, a lot of times we use quadratics to model the shape of things, but the hard part about this for us would be, if we didn't have this equation in the original problem, we would have a very difficult time completing this problem. And there are ways that we can generate this, and we'll get into these more later, okay? Now we're just kind of studying and analyzing the quadratic function, looking at some applications. Later on in your math career, you'll actually learn where do I get this equation? Where does that come from? So applications of quadratics, we're really going to try to dive into this a little bit. And it's actually a very cool thing. Like I said, a lot of what we'll do is involving projectile motion, the actual motion of an object. This is a case where we're actually using a parabola, a quadratic, to model the shape of something. So cool stuff. I hope you guys have a great day. We'll see you next time.